Hi, today I got a very nice question from a customer. He asked how he can calculate the eigenforms and eigenfrequencies for a simple beam. I think to write him some tutorial is not very productive way. Therefore, I will create a small video. My name is Ivan Beleš and I am support engineer for SCIA and Idea Statica. So, and jump directly in SCIA Engineer. We will create a new project, a very simple one. And in this project, I will activate steel as material, and I will use frame XZ model. This is because it's simpler than this general XYZ model, and I don't need to care about the supports in Y direction and rotation of the beam, and so it's much simpler. In the functionality, first we can deactivate everything and activate only dynamics. In the dynamics, the modal and harmonic analysis is always activated, so you don't need to turn it on, and you cannot turn it off, so it's activated. And we can create the model. Usually, please, because this is a model, this is a tutorial for really beginners, probably. Save your model, because if you don't save your first file or the first time save file and something happened, then you have nothing. There's this autosave and creation of the bug files during the save are active after you save your first file, or after you first save your file. So if you don't have the file, then SCIA don't know where to save these files. So you need the name. We start directly with structure, go to beam, because this is simpler. The length is 9 meters, and I will change the cross section because this is tutorial for beginners probably. So I will use a new cross section, HEA and 300. This is my favorite section. It has no issues with stability, so therefore I like it. I did it 2 times, sorry. I have to talk less. Okay, so, and it's 9 meters, that's all. The beginning, you can click everywhere on your screen where you want, but simply write 0, enter, then it's 0 point, and escape, escape, escape until it's not violet. So we need supports. We are in structure, and we need the support in nodes. I will only deactivate the support for rotation around y-axis. Select both nodes and escape. So the second one we will make movable in X direction. So from rigid, change it to free. Okay. If you need the dimensions, you have dimension lines, but I prefer to use the line grid, 9 meters long. In line grid, you get also these labels. If you want to turn them off, if you have a nice 3D grid, for example, we have also the height, and you turn them off, then you get the dimensions. But if you have only one line, then these dimension lines disappears after you deactivated labels. So therefore, it's better to activate label and change the height to 0. Then it's better. And we have dimension lines and we don't have the labels. So, and we put it here, and escape, escape, escape. Escape is end of the command. You can also define that the right mouse button is the end of the command if you want. So, and we have to leave, you see there is a text. grids mode is on. You can select only grids, click here to exist the mode. So we have to deactivate it. And now we are again back in the structure and I can select the members. This is also a common question if somebody starts with SCIA Engineer. I will deactivate the dot grid, and we need for the calculation of the eigenform masses, but usually you don't input masses. Usually you input loads, and SCIA Engineer recalculate these loads into the masses. So we need load cases. Load cases are here in the libraries. Load cases, Control L usually. So this is G1. I use G1 for the name. This is sulfate. Okay. And now I will create two load cases. One with line load is permanent and standard, and second one, let's say the name is P, is our point loads, 2-point loads we will input. Okay, these are load cases. Now I can input the loads, so I change this input bar to loads, and we are in the load case line load. Probably I switch me on the right bottom part because we will use this menu often. G2, this is the load case where we are at the moment and where the loads will be placed after we input it. So we go to line load and let's say minus 10 kilonewton. What is important is that the direction must be Z. The value must be a minus value. System has to be global coordinate, GCS, global coordinate system. And the location must be on length. If these things are defined, then this force will be recalculated from kilonewton to kilogram. The acceleration is defined in the project. It's usually 9.81. So this is defined. We don't need to select the member because it's only one member in my model. And we can simply change to another load case and input these point loads on 1D member. Is, let's say, minus 20 kilonewton. Is in global coordinate system. The first position is 0.333, and we will repeat it 2 times with the distance 0.333 to don't input 2 times the same thing. So it's done. So we have loads. We could calculate the standard linear analysis, but for the dynamic analysis, we need masses. So we need masses. Masses are collected in mass groups, and mass groups are collected in mass groups combinations. So first we need mass group combinations. So they are in the libraries, dynamic mass groups. Sorry, mass groups. Mass group 1 is from mass from self-weight. And it will be automatically recalculated after you change the model. In the past, it was not necessary to create a mass group from self-weight because in each mass group combination was the self-weight automatically included. It was issued to exclude it from there, but now you need it. In the version 25, you need the mass from self-weight. It's better because you can create also models where you don't have the self-weight. So second is mass from line load, line load, and it's from line load, it's everything. Ignore all these buttons. They were important in the past because in the past it was not possible to activate this button, keep masses up to date with loads. So after each change, some years ago, I don't know, it was necessary to delete the masses and create it and generate them again. So no, it's fully automatically everything. You need only the loads. And mass group 3 is mass from point loads. Correctly? Yes, and it goes from point load. So let's check it. G1, G2, and P. Everything correct? Masses. Okay. So we have the mass groups and we need mass group combinations. Why? Because, for example, if you have a building, usually you have one combination of masses. You have one situation for which you calculate the earthquake analysis. You have the self-weight, you have permanent loads, and with Psi2 or Psi-A, you have the variable loads. But you can have also, for example, a pool there, swimming pool, or you can calculate, for example, silos or bunkers. They can be full or empty or half full. So you can have different situations of masses, and you don't want to calculate for each this situation a new model and then look where I get more utilization for the steel members or more reinforcement for the concrete members. So you can create more mass group combinations, and then you have more situations, and for each of these situations you can create earthquake load cases, and then SCIA Engineer creates an envelope from everything. So you have one model with all these situations. So we need these mass group combinations, and we will create two of them. So the first one is with the self-weight and with the line loads, all with the factor 1. So I don't play with these factors. We write this is self-weight with line load. And the next one, we will exclude the line load and import the point loads. So, and this is self-weight with point load. So I have two situations of masses, and I can run only one analysis. So that's almost everything what we need for standard structures. If you have such simple structure like this one, where you have only one member or one column, then you have to define more finite elements, because one element means two nodes. Usually one of these nodes, for example, for column is in support. So you have only one node with one mass. So you can get one eigenform. And if you are in space, then two of them. So, but we need more of them. So therefore we have to create more finite elements on the members. So I go to the calculation mesh and mesh settings, and then we can say how much finite elements on one 1D member with average length we want to have. For example, we have the shortest member is 1 meter long, and the longest member is 10 meter long. So the average value is 5.5 meter. If we say 10 elements, then we have 55 centimeter, the length of one finite element. So on the shortest member, which is 1 meter long, we get only two elements. On the longest one, we get 20 elements. So this is the average number of 1D mesh elements on a straight 1D member. This is not average number, is a number of 1D mesh elements on a member with average length. So should be written on another way a little bit. If this is not enough, for example, you want to have more elements on the shorter beam, so you don't need to increase this number. You can say my longest element is, for example, 20 centimeters. Or there is a manual way how to create the mesh refinement. You can put it also on members or on nodes. And so there are also another ways if you need something special. But we need only this 10 finite elements, that's okay. And we look also on the solver settings, calculation mesh, solver settings. There is one part for the dynamic. There is the solver. In the past you had more solvers, but they are not necessary. Use the Lanczos or polynomial. Usually use Lanczos only if you get some error message that the Lanczos is not usable for your type of calculation or your type of model, then change to the polynomial. Number of eigenmodes, we have 10 elements, we can have 10 eigenmodes, that's okay. Nodal mass matrix is usually diagonal only if you calculate, or if you have eccentricities, for example, in your masses or in members, or if you use this improved reduced system for buildings, for calculation of earthquake, then you need this consistent matrix because you need also the eccentricities. But for us, it's not necessary. Okay, if you didn't save your model, then it's a good time to save the model. We can continue, run the calculation. For the case that you have also dynamic load cases, harmonic load cases, or with the response spectra method for earthquake analysis, you don't need to activate extra the modal analysis. If you activate it, nothing happens, but you don't need to do it. But if you have only mass groups combinations, then you need to activate it. Otherwise, it will only the static analysis will be performed. So activate it, and if you don't see it, this modal analysis, that means you forgot to input the mass group combinations probably, or mass groups. So run the calculation, wait few seconds. I move to the right top corner. So, and now we can check the results. Okay, I go to the bottom. First, where we are, what we see on screen, we see the masses and also the loads. You can change here from load cases to masses, and then you see only the masses. And with the right mouse button, view settings for all entities, load masses, you can activate the labels, for example, if you want to see how much is it. So, and if you want to deactivate it, right mouse button, view settings for all entities, and you can deactivate the masses. But there is also, okay, that's okay. We will deactivate it. We can go back to load cases, it doesn't matter. And check the results. So we are finished with the calculation. So we have a table with the eigenfrequencies if you want. You can put it into the engineering report. So what we get is the frequency and the time. That's all. And what we also need are the deformations, but not from load case. We need it from mass combinations. This is the first situation with self-weight and with line load. So it's 3.58 Hertz is our frequency. So that's the eigenform. And it's better I go to the bottom because we have this legend there. And from the second one, it's a little bit different. So that's all. Don't let you irritate with these millimeters. It has no units. The results from eigenforms are only a picture. You can scale it how do you want. The scaling in SCIA Engineer is that the multiplication of mass multiplied with the deformation, with the amplitude in the node, and sum of all them together, square them, and divide through total mass, you get a 1. This is the scaling which is used in SCIA Engineer. This is a good scaling because it's used in the dynamic analysis for earthquake, so then you get a good values. And there are also another deformations, so I will deactivate the units because they have no sense in these results, and then you get it on this way. And for example, some another eigenform. So that's all. It was a very short and simple tutorial. Thank you very much and have a nice day. Bye.